All right, welcome to the Explainer. So today we're going to dive into a mathematical tool that's been around for literally centuries, but is now kind of quietly powering the entire AI revolution. It's called optimal transport, and its story, wow, it's this perfect example of pure abstract math just waiting for its moment to shine, finding its killer app decades, even centuries later.
So it all kicks off with this really simple question, something first asked over 200 years ago. Picture this. You've got a pile of dirt, right? And you want to build a sandcastle. What's the absolute cheapest way to move all that dirt into the shape of your castle? And by cost, we mean the total distance traveled by every single grain. This simple puzzle, believe it or not, has some seriously deep implications for the tech we use every single day.
Right, because obviously we're not just talking about dirt here. In the world of math, that pile of dirt, well, that's what we'd call a probability distribution. And guess what? So is the castle. Optimal transport gives us this amazing framework for comparing any two shapes of data. Doesn't matter if they're clouds of data points, all the pixels in an image, or even the odds of certain words appearing in a sentence. It's all about finding the absolute path of least resistance to turn one shape into another.
Okay, so let's rewind and start with the original puzzle. It was dreamed up by this brilliant French mathematician, Gaspard Monge, way back in 1781. I mean, his immediate problem was practical. He was thinking about moving Earth around for military fortifications, but the question he asked was so much bigger than that.
So check this out. If your pile of dirt and your castle are just, points on a single line, the solution is, well, it's just beautiful. It's so elegant. All you have to do is sort the points in both lines. That's it. Then you just map them up. The leftmost speck of dirt goes to the leftmost spot in the foundation. The second one goes to the second spot, and you just keep going. And from a computer's perspective, this is incredibly fast. A piece of cake. But here's the catch. That simple, beautiful sorting trick, it completely falls apart. I mean, utterly breaks down the second you add another dimension. Because let's be real, the world isn't a straight line, and neither is the data we actually care about.
See, the issue is with Monge's core idea. He insisted on this really strict one-to-one rule. Every single grain of dirt has to go to one and only one final spot. But what happens if you have one big pile of dirt and you need to use it to build the bases of, say, two different castle towers? How do you do that with a one-to-one map? You can't. Suddenly, the problem as he framed it just becomes impossible. There's no solution.
And get this, for almost 160 years, this was a huge roadblock for mathematicians. The problem was elegant, sure, but often unsolvable. That is, until a game-changing insight during World War II flipped the whole thing on its head.
So the big breakthrough comes from a Soviet mathematician, Leonid Kantorovich. And his idea was just profound. He basically said, hey, what if we just forget that rigid one-to-one rule? Instead of forcing every speck of dirt to go to one place, what if you could split it up? Send a little bit here, a little bit there. He called this mass splitting.
I mean, this was a complete fundamental shift in how to even think about the problem. So while Monge was looking for this rigid list of assignments, you go here, you go there, Kantorovich came up with a flexible coupling. Think of it like a master plan that describes how much of the mass from any starting point flows to any destination point. It's not about where each individual particle goes anymore. It's about what fraction of the mass goes where. Totally different game.
And here's the payoff. By allowing the mass to be split, this relaxation of the problem, as he called it, guarantees that you can always find a solution. Always. He single-handedly took this problem from being sometimes impossible to universally solvable. It became a proper, well-behaved math problem you could actually get your hands on.
So yeah, this was definitely not an overnight thing. It took literally centuries of progress. You have Mons starting the whole puzzle, then Kantorovich with his game-changing flexible plan, and then another key piece of the puzzle from Jan Brennier in the 90s, who connected it all to some really deep geometry. It's like building a cathedral of ideas, one brick at a time.
Okay, but even with this amazing theoretical foundation, there was still one giant problem standing in the way of anyone actually using it. Even with Kantorovich's brilliant fix, calculating the answer was just painfully, incredibly slow for any kind of real-world data.
You know, the classic algorithms for this, like the Hungarian method,
They have what we call n-cubed complexity, and that's not great. For a few points, sure, it's fine, but in modern machine learning, we're dealing with millions of data points. When n is a million, n-cubed is a number so big your calculator will just laugh at you. We needed a radically faster approach.
And the modern solution, which was really brought into the spotlight by Marco Cattori around 2013, was just brilliantly counterintuitive. He said, okay, instead of killing ourselves to find the single, perfect, razor-sharp answer, what if we aim for one that's just a little bit fuzzy, a little blurry around the edges? And you do this by adding a tiny little bit of what's called entropy into the mix.
And this tiny little tweak, it completely transforms the problem. All of a sudden, you can solve it with this incredibly simple, almost beautiful, back-and-forth process called the Sinkhorn algorithm. You basically just start with a guess, and then you tweak the rows of your plan, then you tweak the columns, then the rows again, then the columns. It's like you're balancing a scale, just nudging each side a little bit at a time until it's perfectly level.
And here, this is the real magic. This is the part that changes everything. Those simple back-and-forth scaling steps, under the hood, they're just a bunch of matrix multiplications. And what is the one thing that modern GPUs are absolutely unbelievably good at? Exactly that. Doing millions of those operations all at once. So this simple algorithm, unlocked by adding a bit of fuzziness, was the final key that made optimal transport fast enough for massive AI.
Okay, so let's recap. We've got a fast way to solve a 200-year-old math problem, which is cool, for the math nerds among us, but why should you care? Why does this matter so much for AI right now?
Well, let's just step back and think about what generative AI is really trying to do. At its absolute heart, whether it's making a picture of a cat or writing an email, the goal is always the same. You learn what real data looks like, and then you try to generate new data that's indistinguishable from it. And to get better at that, the AI needs a good way to measure the distance between its creation and reality. How far off was I?
And optimal transport gives us exactly that. It's not just a number, it's a true, meaningful geometric distance. That cost of moving the dirt we talked about, that's what we call the Wasserstein distance. And it's so powerful because, unlike a lot of other ways of comparing things, it gets the geometry. It inherently understands that moving a pixel just a little bit is a much smaller error than yeeting it all the way across the image.
So this one concept has just exploded, leading to breakthroughs all over the place in AI. It's a core component for training generative adversarial networks, GANs, that create those hyper-realistic images. It's right at the heart of the diffusion models, the power tools like DALL-E and Midjourney. People are even using it now to peek inside and understand how information actually flows through giant language models like transformers. I mean, just think about that journey for a second. We start with a puzzle about moving dirt dreamed up during the French Revolution. It gets a major update from a Soviet economist during a world war, and then it's finally unlocked for the modern world, all because we decided to add a little bit of computational fuzziness to it. And the result? It's now one of the most powerful and fundamental tools we have for building the AI that is shaping our world. This whole story just makes you wonder, doesn't it? What other beautiful, elegant ideas are just sitting there, maybe in some dusty old math textbook, just waiting for that one clever algorithm or that next leap in computing power to be unleashed and completely change our world all over again?